Hello, everyone. Thank you for tuning into this talk. My name is I5s Espinosa, and today I'm going to present some early stage work examining the characteristics, drivers, and evolution of summertime Antarctic extreme heat events. So to start with a bit of motivation, Antarctic heat waves remain relatively understudied despite their impact on surface ice melt, sea level rise, and coastal ecosystems. Here, we present preliminary results of a novel investigation into the characteristics of summertime Antarctic extreme events. So first, using daily maximum 2-meter temperature, we define an extreme heat event as an exceedance of the 95th percentile threshold that lasts for more than 3 consecutive days. The heat wave threshold is defined locally and from a 15-day low-pass filtered daily climatology. The intensity of the heat wave is the maximum temperature anomaly of the event, and the duration is the number of consecutive days above the 95th percentile threshold. And then finally, the frequency is the number of events per decade. So here we're showing the spatial maps of duration, frequency, and intensity of heat events, as well as the skew of the raw DJF temperature anomaly distribution. A few interesting observations. We notice that the intensity is strongly coupled to the skew and the temperature variability, consistent with our 95th percentile thresholding. We also noticed that the skew and intensity exhibit a really interesting ocean and land contrast, with the ocean having negative skew and low intensity heat waves. We believe this is likely because the right tail of the temperature distribution, particularly during the summer, is fixed at the melting point of ice, causing a negative skew and damped variability along the coast and in oceanic regions. We also notice regional variations in heat wave properties. So the Dome Sea sector, which we just heard about, is prone to intense heat waves, and West Antarctica, likely due to its local geography, is prone to more frequent and longer lasting heat waves. Next, we were curious to see how these characteristics have changed over the historical record. So here we show the spatial pattern of changes in frequency, intensity, and duration, as well as the raw temperature values between 1980 and 2022, with stippling indicating statistical significance. So we notice first that the spatial pattern of changes in frequency are well explained by changes in the temperature trends. But we also notice that the trend of increased intensity of heat waves on the eastern coast of the Antarctic Peninsula is unexplained by temperature trends. We thought perhaps that these tendencies may be dynamically driven rather than thermodynamic changes. In order to explain this further, here we examine the impact of the Amundsen-Sea low and the southern annual mode on heat wave properties. I'm showing spatial maps of the impact of variations on the ASL on each property. Specifically, when the central pressure of the Amundsen-Sea low in DJF is 1 sigma below average, we observe statistically significant cooling near the Ross Sea and warming over the Riddell ice shelf. Interestingly, we find that the intensity trend over the East Antarctic Peninsula is explained by a deepening of the Amundsen-Sea low and a strengthening of downslope foehn wind warming events. Finally, I'd like to examine the relationship between atmospheric heat transport convergence, surface energy flux anomalies, and heat waves. For this analysis, we decompose the Antarctic continent into 2 regions: a high elevation region in brown that's above 2,000 meters, and a low elevation coastal region in green below 500 meters. Now, this is a very imperfect decomposition for several reasons, which I'd be happy to discuss later. But for a preliminary analysis, an elevation-based decomposition offers some interesting insights. So here I'm showing a surface energy flux composite for all heat waves at high elevation in the upper row and low elevation in the bottom row. The red line shows the temperature anomaly, and the black line shows the net surface downward flux. And this is for the 7 days before and after a heat wave, composited for the entire region at higher and lower elevation. Interesting, in both regions, we see large positive downward long wave anomalies and large negative short wave anomalies. We also see that at low elevation, sensible heat flux seems to play an important role. Then, when examining the total column vertically integrated atmospheric heat transport convergence, we observe that there's a peak in convergence coinciding with the maximum surface temperature tendency, and that dry and moist components play roughly equal roles in warming. So with that, I want to thank you for your attention. Hopefully this has been just enough to pique your interest, and I'd be happy to take any questions you may have.